All right, let's keep going talking about data design now that we've talked about class diagrams and associations and multiplicity and whatnot. Let's take a look at actually applying some of these to designing a database for a very simple database. In this case, we want to be able to keep track of our CD library, and we were capturing, for instance, the title of the CD, the release year, the band, the genre, and for each CD, we are capturing things such as the track number, the song title, the duration, and notice that it has both of these have a primary key, CD ID, and track ID. So these are primary keys, CD ID and track ID. But notice that the track also has a CD ID. See that? So that one is a kind of like a foreign key saying that I am the track, right, for this particular CD. Right, given a CD, I have many of these tracks. Now this might look like it's capturing everything I need, right? I just have lots and lots of CDs, and every CD might have lots and lots of tracks in there, right? And it looks like it would capture everything that I need. But then we start going through our collection, and we notice that there's some overlap between them, right? We see that, wait a minute, but this author not only is in this band, but this author is also in some other band, right? And then some CDs are kind of like collection of the same tracks of different CDs, but like the best of a particular band, right? That does a collection of different tracks in one single CD, right? And so you might start looking at this and say, wait a minute, I have a lot of redundancy here, right? The same track is being copied over and over and over. It appears, I would have thought that one song appeared only on that one CD, right? I might have had this very simplistic model of this in my head. But once I start exploring this, I notice that actually this track appears in this CD, and that other CD, and that other CD over there, and then by some other band, some revival band that is doing the same track over here. So I said, oh my goodness, this is just a mess, right? This track appears so many times repeated. So when I'm trying to burn some of these songs into a CD, what if the order is completely different, right? Or if I splice together different versions, right? Or different genres, you might have a CD that has different various genres into one single CD. So no longer is genre allows me to capture things like that, right? So genre perhaps should be a separate class, not an attribute. Right, it should be an association as opposed to as an attribute, right? So this would become very, very cumbersome. Again, it depends what my goal is, what kind of things I want to be able to answer, right? If I just want just a collection of all my CDs and what the tracks are in that, that's perfectly fine. This database this schema will do just fine, right? So class diagrams. As we said just earlier, capture the relationships and attributes of different entities. Entities, we're going to be using entities quite a bit. Again, it's another way of referring to things that have identities, right? They have some unique identity that says there's only one instance of this in the world and it's unique, right? And we're going to be using class diagrams to capture these things. Also relationships, we're going to be, as we saw earlier, we're going to be using lines to capture the relationship between different entities, and the attributes will be represented as fields that can have particular values for those fields. And we're going to be looking at strategies to do the conversion between this very high level, pie in the sky, very conceptual model, right, into some concrete representation that we can actually implement in code. All right. So we'd like to see how we can convert this conceptual model into actual relational schema tables. So let's consider this class diagram that we were looking at the beginning of last week, right, where we had students that had names and graduation years associated to a department, right? So a student could be enrolled at most in one department, but one department could have many students, right? But one student had only one department. Also, a department can have many courses. That's the one-to-many, right? It says that there's one department participating in this association, but many courses are participating in that same association, right? We also have here that, oops, where'd it go? Okay. Why did it jump like that? Okay, whoa. Why did you do that? You want to skip 20 slides forward. Okay, let's go back here. And we see that one course can have many sections, right? So in here, actually, I think we have like 2 or 3 sections for this course. So you have only one instance of this course, but you might have 3 instances of a section. And also, a student might be enrolled in many different sections of many different courses, right? So the enrollment tables, notice that there's a one-to-many and a one-to-many, right? That means that for one student, there might be many different records over here that tell me that I might be enrolled in 3 different courses, right? In 3 different sections. So one student here, you might have 3 different records here, each one of them pointing to different sections in this section table, right? So let's I'm going backwards. So let's look at some of this a little in a more graphical way in a couple of slides ahead. Cardinality we mentioned earlier. It could be captures how many of each instance participate in the relationship, and it's denoted as n and .m, and it's annotated next to each one of the classes to denote how many are participating. One of the more common ones is the many-to-one. I can't figure out how this is moving. Okay, there we go. Many-to-one is one of the relationships that tell me on the star end that says that there are many students, right, that are participating in one department. Right? Given the department, I can tell you which students are in that department. If you tell me another department, there will be a different set of students. But always we have, for any one of these, we can have lots of those. Okay, that's how this is read. This is referred to as a many-to-one, or you can read it the other way around, as a one-to-many relationship. Okay, or you can have a one-to-one relationship where, for instance, in this case, you can have that the student can only have one single permit to park here in the university grounds, right? There's only one permit. So if you tell me one student, there'll only be one instance of a permit for that particular student, okay? Or you might say that maybe there is no permit for the student, right? If they don't apply for a permit to park, we don't give it to them. So we might say, instead of denoting 1, we might say 0.1, meaning that it's optional, right? There might be no permit associated to this student. If we say 1, that means that there has to be one permit for that particular student. Or there might be a many-to-many relationship, right, where many of one side are participating with many on the other side, right, where you might be a student that can be enrolled in several departments, right, maybe for a major and a minor, right, and so if you give me one student, there might be different records here, multiple records, that are associated with that one student, right? But if I go the other way around, if I give you one department, there might be many students that are associated to that one department. I think a better example might be actors in movies, for instance, right? An actor might act in many different movies, right? But if you give me one movie, then I can tell you how many actors or which actors participating in that particular movie, right? They're also many-to-many. Yes?
So this isn't one of the many-to-many you'd want to normalize. This is a good many-to-many.
Yeah, this is a good many-to-many. Well, it depends on the business logic, right? If the business allows, says that a student can participate in many different departments, then certainly you would capture this. Typically, when you're going to implement this in a schema, you can't actually implement it, right? Because there's no way to have multiple foreign keys, right, referring to the same primary key, right? A multiple primary key. So you can't have many-to-many. If you're looking at MongoDB and other ways to represent it, yes, you could do that over there, but not in relational schemas, right? So typically you do want to normalizes and put we'll call it a reify a little later. There's one of the questions in the assignment asks you, do you need to reify this? Okay, so in this case, you would need to reify this, right? You would have to put a mapping table in between here, right? That would allow you to create this mapping, right? Such as we did earlier, right? This here, this enrollment here is a reification, right, of a many-to-many between students and sections, right? Students and sections, you can have a many-to-many there. See that, right? But you can't actually implement that on a relational schema. Right, you need a mapping table in between, and that's what enrollment does, right? And additionally, not only does it implement the relationship, it describes the association by adding a grade. Not only am I telling you that you are enrolled in this section, but I'm also adding additional information about that association, right? That this is the grade you got in that relationship. Okay. Right, so one-to-one. Yeah, okay, we did that already. Right, many-to-many students and departments. Relationship strength. So depending on these, whether you are confident on how many are participating or you're not confident, right? Depending on how strong you feel about how many are participating, we named each side of the relationship either as strong or as weak. Okay, strong associations are those that we are certain that one or two or three are actually going to participate in that relationship, right? On the other side, where we don't know if somebody's actually going to have participating in the relationship, maybe it's optional. It's not. We don't even have a record for it, right? Or we might have one or two or many. We don't know how many, right? We say that that side of the association, we call it a weak association, right? So we talk about associations being strong, or strong, weak, or weak, strong, or weak, weak, right? Depending on what you have, those four types, right? So many-to-many, we say that it's a weak, weak association. We don't know how many on one side, and we don't know how many on the other side. It might be there is no relationship. Just you have 0 instances over here associated with 0 instances over there, right? They're complete, or you might have lots of associations. We don't know. 1-1 is certainly strong, right? We know that there's one on one side and one on the other, right? So we say it's strong. These are all the examples that are available, and the cardinality that is associated to this relationship. It's just nomenclature, right? And how to speak the jargon. Now, right? So it's very useful, right, to represent these relationships as UML class diagrams, because visually understanding something is so much better than trying to follow classes and pointers and foreign keys and primary keys, right? It's so much easier when you have a graphical relationship or a graphical representation, right? We will say that a picture is worth 1,000 words. So just by looking at the graph. It's very easy that we can answer certain questions, right? That if you tell me the students, I can tell you what department they're in. But if you tell me the department, I can tell you which students are there, right? Or if you give me the department, I can tell you which courses are being taught, right? If you give me the department, I can give you a listing of all the sections for that department, right? Or if I give you a student, I can tell you what courses, following the enrollments, the section in the course. I can tell you all the courses that particular student is enrolled, right? We can answer those kinds of questions by navigating, right, all those associations, right? Just by looking at graphically, right? If this were instead a relational model or schema, it would be very, very hard, right, to go through all the create statements, right, and follow all these primary keys, foreign keys, to try to understand mentally how do I follow, right, from one to the other. Not until somebody gives you a graphical representation and says, makes sense, right? I see how you can get from one to the other. Right? So it's usually when you're tasked to manipulate or do anything with the database, the best thing is to first ask, please give me a UML or an ERD diagram so I can understand what's going on here. And there's plenty of tools that you can point to a relational schema, right? And it'll reverse engineer, right, what these diagrams are, right? So here's let's explore this a little further. Notice the cardinalities here. So notice I've highlighted them in red. So let's just try and traverse and follow along. All right. So let's consider first tables or records that would be represented or implemented using this schema. So for instance, here you have students. You might have many records for a student, right? So here we have Alice, Bob, and Chuck, A, B, C, and their SIDs, right? 1, 2, 3, 3, 4, 5, and 4, 5, 6. Everybody okay? For department, we might have 2 departments. The IDs are 10 and 20. So you have CCIS, you have the Department of Law. Over here we have different courses, right? We have the web development and software engineering and their CIDs, and notice that they have here the department that they're being taught at, right? 10-10, meaning that somehow we know that the relationship goes to that department. But notice that following those records and reading that 10 is so much harder than just drawing a line, right? And saying that's one to many, right? And so considering this snapshot of data, right? Let's try and look at this individually, right? What does it mean? So notice that we have Alice here that has a 1, 2, 3, right? So there's one Alice over there, but notice that Alice is enrolled, has 2 enrollments over here, right? And this is what we mean, a 1 on that side, and we have a star on this side, right? That's what we mean, right? There might be many on this side for each one that is over there, right? Notice that Bob also has an enrollment, right? And Bob got an A minus. And Chuck has an enrollment, 4, 5, 6, and Chuck got a B plus, right? In that particular enrollment. But Alice has 2 enrollments. Everybody okay? Right? If you follow along, notice that we also have a star and a 1 between the enrollment and the section. To look at that, notice that we have here these 3 different students, right? Certainly 1, 2, 3 refers to Alice, 3, 4, 5 refers to Bob, and 4, 5, 6 refer to Chuck. All 3, right, have enrollments, and all 3 are enrolled in section 5, 6, 7, right? Again, this is what we mean by a star and a 1, right? There might be one section, but there's a whole bunch of these records on this end of the relationship. Make sense? Right? And we keep going along. And we see that there's a star on the section side, and we have a course. And what that means here in this particular case is that notice we have 2 5, 6, 10s and 2 4500s, right? Meaning we have 2 folks that 2 sections 321 and 321. That's not right. That makes no sense. Let me change that. So this might be maybe 432. Maybe that's what I meant. Did I do the same thing here? Yes. Oh, I must have broken it at some point. Okay, there we are. Oh, fix it here too. Here we have 2 sections, section 321 and section 432. Both of them, right? Both of them are 2 different sections of the same course, web, right? 5610, right? And finally, both courses, web dev and software engineering, they're both being taught. They're both courses that are being offered by the same department, 10 CCIS. Yes? That makes sense? All right. Yes?
So in the enroll table, if we make an entry like 3, 4, 5 and registered for 6, 7, 8, even that is a valid entry.
Sure. We're saying that Bob is also enrolled in 4500, right?
Like 2 sections. So, like, how do we enforce that for one course a person can only, enroll for 1 section? So, do we have to create?
Sure. Yeah. We'll see that in a minute. But we can certainly what we could do is that we take both the student ID and the section ID, and that the combination of both, we say that it's unique, right? So that if you try to tell me that that same user or same student tries to enroll in the same section, the database would not allow to break that uniqueness. Is that what you were asking? I'm sorry.
Not the same section, different section but the same course.
Different section, but the same course.
That's probably when they would link it according to grade. If you got higher than a C,
Right.
you can't take it. It's sort of like for people
Okay.
who fail a class and need to repeat it. So
Okay.
you would just write another query that would say, if student in enrollment, if unique
Okay.
got C, you can't register.
Oh, okay.
Oh.
All right. Yeah, you would need that additional reference into that table if you want to make it unique. Also. Yep.
It's a business case.
Yep. Perfect. So notice that certain things cannot be answered, right? Depending as you follow along, right? So for instance, that one of those things are not supported in our data model. If a student changed majors, right? Well, that certainly is not captured anywhere here. If there's a relationship between a particular professor advising a particular student, that's not captured here either. And so if you can't answer some of the use cases that were originally in the requirements document, then your database is inadequate, or it's not. It doesn't have it's ultimately measured against the original use cases for which this was originally designed for, right? So that's why we mean the use cases, right, drive everything else, right? The business rules, like for instance, we don't allow this or that or the other, right, would drive which primary keys and foreign keys and uniqueness relationship do we need to enforce those rules. So we want to be able to first, again, go through the UML process of doing the high-level design, and eventually we need to implement it as a concrete relational model, right? We want to be able to convert class diagrams into relational model, classes into tables, attributes into fields, and relationship ultimately into foreign keys and primary keys, right? So we'll like to do that. So let's look at transforming some of these, right? Let's consider the following classes that we looked at earlier. We had CDs, tracks, and lyrics. And if you remember the nomenclature, the bold, underline were primary keys, and I believe bold, italic means that it's a foreign key. I believe that's what it was. I noticed lyrics. It's bold, underscore, and italic. That means that it's a primary key and it's a foreign key at the same time. All right. So here we have lyrics table holds the lyrics and the author of that particular track, and it's both a primary and a foreign key, meaning that giving a track, there's only one lyric for that song, right? Right. So we have many track records for one CD and one lyric per track, right? Since we don't have any constraints on the CD records, then that means that it could be several tracks, 0 tracks or more tracks, giving a CD, or that a particular track could have lyrics or not. Okay. So here's some graphical representation of the same thing, right? Where you have giving a particular CD, you might have different tracks for the first CD or different tracks for the second CD, and that there's a one-to-one relationship between the lyric and the track. Right? Give me one track, I'll have that one same lyric for the same CD. And the way we implement them in a relational database is that we're going to be using what are called primary keys and foreign keys. Right? Notice that the foreign keys and primary keys are not captured in the high-level UML conceptual diagram. Right? Notice that the fields that we use for the relationship are not captured here. Notice nowhere do you see IDs or CIDs, right, or track IDs, right? Those are all implied by the line, right? They're all implied by the cardinality, right? So you would have because we have a star on the conceptual model, that means that that's implemented using a foreign key, right? And because there's only one on this other side, it's implied that it's implemented as a primary key. So first, we'd like to be able to convert, given a relational model, into a class diagram, right? So for instance, if you have a table that has different fields in it, we would like to create a class diagram that is equivalent to that relational model, and vice versa. First, let's look at a relational model and convert it into a class diagram. So for instance, the algorithm that goes something like this, right? We create for every table one class. So that's easy, right? So if we find every one of the tables gets a class. From there on, we need to be able to now add the relationships between these, right? If there's a foreign key, on one of the tables, that's going to be converted into a multiplicity, right? If there's a primary key on the other end, that's going to be converted into a 1, right? That becomes the multiplicity. Now it depends if the foreign key on the weak side, right? If that foreign key is also a primary key, right? Then it gets converted into a 0 or 1, right? Which is an optional, right? Meaning that there's only one of these that can participate in that relationship, right? And finally, once we've added all the fields for the relationship, we need to then add all the other fields, right? The usernames, the passwords, the first name, the last name, the normal attributes are added then into the classes, right? So for instance, if we apply this algorithm that we have the schema, we have these tables and we have these fields, you would end up presumably with the class diagram that we started with, right? So here we have five tables. We have 5 classes. We have the department. Let's see. Notice that the student, the major ID, is a foreign key, right? That is referencing the department. So that means that there's going to be a star, right, on the side of the student, and there's going to be a 1 on the side of the department. That's exactly what we have, right? Also, notice that the section has a section ID, but it also has a course ID, right? That it's referencing right. This is referencing the course, right? So that means that this is going to have a star on the side of the section, and there's going to be a 1 on the side of the course, right? And that's exactly what we have, right? We have a star and then a course and a section. And then finally, we have the course has a foreign key that is referencing the department, right? So that means that the course is going to have a star on the side of the course, and then they have a 1 on the side of the department. And this one is a little bit weird, right? We have 2 foreign keys, right? One referencing the section and one referencing the student, right? That means that it's going to have 2 stars, right? Right, one on the side, both on the side of the enrollments, but next to the association, and so you're gonna have a star leaving the section, going over to the 1 on the section, and then you're gonna have another star leaving this enrollment from this referencing the student, and there's a 1 on the side of the student, which is exactly what we have here. That makes sense? This doesn't cover everything, right? There's several other edge cases that are not considered here, and we'll cover those as we progress. Okay? Right. Right. So obviously, a diagram is so much better to read. Again, it's always a better idea to transform up to the conceptual model, do your modifications there, and then transform back to the relational. We can go the other way around, right? Given a class diagram, we can generate the relational schema, right? Again, 3 steps. The first step is for every class, we generate a table. So there's pretty much a one-to-one relationship between the class and the table. And then all the attributes that were in the original class, they're just going to become fields in the schema, right? So everybody gets a primary key, right, by default. Right? If there is a natural key, right? If a class has a key that uniquely identifies it, don't generate an artificial one, right? So for instance, if you already are using the username as a unique identifier, don't go and create another unique identifier, right? If you can help it, right? Or if you're using the email, right? If there's a field email and that is enough as a unique enough, then use that as your primary key, right? Also for the weak strong relationship, everywhere where you see a foreign key, right? There's going to be that's going to be the weak side, and wherever you can see a primary key, that's going to be the strong side, right? You're going to have ones and stars, right? So the same thing. If you start here, you end up with the resulting schema. Obviously, we've made some major assumptions here, and also we haven't done everything, right? Notice that, for instance, here the department name probably is unique, right? So probably we don't need the DID. So we can scratch the DID and just keep the department name, right? And wherever you see anybody referencing the department ID, we could just substitute by the name of the department. Right? Again, if the department name is unique enough. Right? Also here, the enrollment, already, if we make the rule that one person can be enrolled in a section at most once, right? Probably the combination of a student ID and the section ID is already unique enough, right? So we might not need an EID, right, that uniquely identifies this section. So we could probably do a compound key here using the combination of those two fields, right? And then we can remove the EID. Nobody's referencing the enrollment anyway, so it doesn't need to have its own primary key anyway, right? So it's enough to perhaps just take those two and make it a primary key, the combination. The course ID, probably the title of the course is unique enough, right? And perhaps we could go along with just removing the course ID and just keeping the title as the primary key. And then instead of using course ID to reference the course, we can just reference it using the title of the course, right? Again, it depends, right? Depends on the business, depends on whether you actually need unique identifiers for this. Nevertheless, here are some of the steps that you go about simplifying it a little bit, removing the department ID, removing the major ID, and just referencing the name of the major of the department. The permit ID, since the permit ID is already a one-to-one, meaning one student gets only one permit. Yes?
But you would keep the permit ID like for here, where we have a limited number of permits you can give out. So that would be a reason to keep permit ID.
Okay, sure. Yep. You could use it like a count, right? And say that there can be at most this many.
Right.
Yep. So in this case, we are using student ID as long as there are as many spaces as there are students. Okay. Also, natural keys, right? Perhaps we don't need EIDs. And for the course, again, we're using the title for uniqueness, right? Again, there's some limitation. It does not consider many-to-many, right? Or one-to-one. It doesn't include those, right? It only deals with one-to-many or many-to-one, right? So we'll look at some other of these edge cases a little later. All right. Let's take a break, and we'll come back right after these messages.